Our next speaker is Erik Waingarten. Erik is a postdoc at Stanford and is currently a research fellow in the High Dimensional Probability program. Erik.
Okay, thanks, Prasad. So in this short talk, I want to tell you guys about an algorithms problem, which is taking place in some high-dimensional metric space. So the algorithms problem is the approximate nearest neighbor problem. And I have this picture here to explain what the problem is. Basically, we receive a data set, and think about this as just n points in some high-dimensional space. And what we want to do is we want to pre-process it into a data structure such that we can do approximate similarity search. So what this means is that after you pre-process your points, there's going to be a query which comes in. This is a blue point in the center labeled Q. And the promise is that there exists some point from the data set within distance r from the query. So r is some parameter, and x here is the point from the data set, which is closest to q. And now the task is to return any point from the data set within distance c times r from the query. So in the picture here, this is the point x hat, so distance c times r. So if c is bigger than 1, then you're returning an approximate nearest neighbor to the query point q. And this problem sort of shows up, and it's really parameterized by how we measure distances in this space. So let me tell you about maybe one of the most well-known results in this area, which is when the underlying metric space is the L1 distance. So this is in the next slide. This is a theorem of Indyk and Motwani from 1998, and it really shows like the goal of what we really want to from these data structures. So in particular, when p equals 1, so this is the metric space L1, where you take the sum of absolute values, we can basically design a data structure where the approximation factor c is 1 over epsilon. The space is slightly superlinear, basically d times n to the 1 plus epsilon, and the query time is highly sublinear. So we're trying not to scan through the entire data set. Think of epsilon as being like 1/2. This is time complexity square root n. Okay, so go to the next slide. On the other hand, when we think of p as being something large, like the L infinity distance, suddenly the best known algorithms that we have running in sublinear time have to pay a large factor in the approximation. In particular, for p equals infinity, the best algorithm that we know that runs in sublinear time has complexity which is log d. Okay. So this is much worse than the constant approximation we got from when p equals 1. Okay, so the next slide. Okay, so this is basically a picture of the state of the art and where I explained the sort of the new result. So we have in the y-axis here represents the approximation factor, and p represents the x-axis. So we go from p equals 1 on the lower left, getting the constant approximation, to p equals infinity all the way on the right. And this basically, this curve that is supposed to be sort of like log d is supposed to indicate the conjectured optimal algorithm. And the new result is that we can actually match this conjectured optimal whenever p is bigger than log d. This is like some technical reasons. This is the new result with Alex Andoni, Sasha Nikolov, and Ilya Rajenstein. And at a high level, you can think about this as kind of interpolating between the case for p equals 1 and p equals infinity, which even though algorithmically look very different, there is a way to smoothly trade these off. And then I'm highlighting this green region here because this is the open problem. This is still this area where we don't quite have what the conjectured optimal algorithm is. Yeah, so that's everything.